let me also see permutation. So we will try to follow Artin here. Permutation matrices, obviously there is a lot of things one can do with these objects, but mostly they are basically permutations. But yeah, let us. One thing which I will say, which you may not, maybe you, but you will realize this sooner or later, that permutation matrices, I should say, permutation matrices are and you can look at them as an algebraic copy of permutation. Okay. And they can be very useful to sometimes prove a lot of combinatorial properties of permutations. Okay, they can be more easily proved when you go to permutation matrices. Okay, so what are permutation matrices? So let's say this. You can just, I don't know. So yeah, let me say it in an abstract way slightly. Okay, so you know what is Sn?
Yeah.
Okay. So Sn is your correct. Yeah, so it's the group of all permutations. So just take the collection of all permutations on n letters, and you can look at them as functions from n to n, which are bijections. So you can compose them, inverse everything. So it's a group, right? And then you know what is GLNR.
GLNR matrix,
This
they
would
are
be non-zero. So these are all invertible matrices, invertible n by n matrices with real entries. So this is the equation. Right. So what we want to do is we want to take a permutation. So I'll denote it by sigma. You can write it as F also. But yeah. So you denote it as sigma, and then with sigma you want to associate a matrix. With every permutation you want to associate a matrix. Okay. So what is the most natural matrix to associate to a permutation? So it's very simple. There are two ways maybe to do it, but if you do the row oriented way, then like this. So you write it one minute. So I can say it in words, of course. Ith row has 1 in sigma ith column. Okay, and 0 everywhere else. Okay, that's it. So in the first row, maybe I can just write that the first row is basically E sigma 1. Right? This is the elementary vector which has 1 in the ith, 1 in the sigma 1th entry. And similarly, so that's the first row. And similarly, the second row is, let me just do an example. But so is the definition okay? So we are putting a 1 in the sigma I position in the ith row. Okay. So if you want to take an example, me just put an example. Take n equal to 3, and you should tell me what the permutation is. So I'll just write it in the cycle notation. This. So what is the permutation? You can read the cycle notation. Have you done that? Yes. No? Am I audible?
Sorry, yeah.
Okay.
1 goes to 2, 2 goes to 3, and 3 goes to 1.
Right. So now tell me what the matrix will be.
I don't know.
Don't know. Use the definition. So I've given you two definitions. You can use the verbal definition. Just read the verbal definition and try to see if you can catch it. I just want to try yourself. Ith row has 1 in the sigma ith column. Right?
Not getting.
No problem. So here you write. So this is your sigma. Okay. So tell me what is sigma 1?
Sigma 1 is 2.
Okay. What? And then, so you know this.
3, 1.
Right? Now you read this. Now read it again and try.
Ith row has 1 in sigma ith column.
If you find it difficult, put I equal to 1 and read and then write it. You can do it.
Okay, first row have 2. Sorry, first row has 1 in second. Sigma is second position.
Mhm.
So second column will be 1.
And what else is written? 0 everywhere
And
else.
yeah,
That you can write in the end also, but correct.
okay.
And other?
And then for sigma 2, in column 3 there will be 1. Second column, third row, second row, third column, 1. Yeah. And the last is the first one is 1.
Very good. That is it. Okay. You have to break it down. We don't understand things so easily. When I read something, sometimes one line I have to read it 10 minutes, then I understand. Okay. So and whole day, maybe 5-6 pages we read. If it's a thing, a decent thing. If it's hard, it's people lesser. It's like that. You have to constantly work. That's it. So now you understand permutation matrix.
Yes.
Now let's see a few things which I can say, and then we will look at what is there in the book. Okay, if there is some other interesting things. Then I'm erasing this. Now so now you can see that it's very natural, right? Just row by row you go and you put it in it's like abacus maybe, yeah. But now let us try to feel this slightly in a more interesting way. I have yet not maybe defined. So what you saw, that was a permutation matrix. Okay? What are the collection of all permutation matrices? Look at this phi, this function, and permutation matrices. I just write it here only. It is just the image of this function. Is the collection of all permutation matrices. Right? So every permutation, you look at the matrix. Those matrices are called permutation matrices. Collection of all those matrices is the collection of permutation. Okay. So every 0-1 matrix is not a permutation matrix. You understand that? Yeah. So now you tell me how many permutation matrices are there?
How many permutation matrices in?
Yeah, in n. Yeah. in Sn from Sn. For n, how many permutation matrices of size n?
In fact,
Yes. Yeah. In fact, it's very, very simple. Yeah. Now there is a whole series of interesting questions that can come here, but I am avoiding it for now. Okay, because let's see, maybe in the right setting it will come. So now let us ask some questions. Let's say to see some things which are useful from matrix angle. So let this is one of the very important features, that A be a permit, or maybe I'll just now, whenever whatever matrix I write here, will assume is permutation matrix. I'll not write it. Okay. Can you see? Can you show that A transpose is equal to? Okay, so maybe I should not ask like this. Okay. So can you show that phi is a group homomorphism? Maybe we should do this. This will take care of a lot of things. It's not done in chapter 1, but you have done group theory, so it's better to do it from. Show that
so,
phi is a group homomorphism.
Sn to GLNR.
Yes, that map. Once you show that, a lot of things will get taken care of on their own. We don't have to keep writing like this. We should move in a more mature way. So phi is, it should be, if you just show isomorphism like that. So let us see, because maybe, yeah,
We have to take the elements as phi, a sigma of Sn.
you can take it anything. I'm just denoting it by 6. It's just a notation, right?
Okay, so um, so there is identity
Uh-huh.
that is phi e equal to I.
Mm-hmm.
I is belongs to GLNR.
Mm-hmm. That goes to I, right? Identity permutation goes to identity matrix.
Yeah.
That is clear.
And then we will take two elements, let sigma and wait one minute, GLNR. Take two elements from Sn. One is sigma and another one is tau,
Okay.
and apply phi on that.
Phi
We
on
have
what?
to show
Wait, on which? On what? You took two
phi
things.
on sigma tau.
Sigma, okay. So sigma compose tau. I'm just writing it composition sign here.
Okay, okay. Okay, you're taking tau. Okay, okay.
Doesn't matter.
No, it's okay. I just take the it's called phi into tau composition sigma, and we have to show phi of tau composition phi of sigma.
Yeah. And here the composition is matrix multiple.
Hmm.
Right.
Okay. So phi of tau is we take phi of tau is m sigma,
Phi of
and
tau is okay.
phi of sigma is N.
This is okay.
1 minute. Yeah, that like that.
Yeah.
M into tau. This is sigma. Now
Now we have to do something, right? Till now we are just writing, right? This for that, sigma and tau, we're taking, we're writing. But you do something also.
so we have to show that m tau sigma equal to m tau into m sigma.
Right. But okay, that's the same. Yeah, that we're just writing
But
the same
I
thing.
was thinking how to show it.
Yeah, I know.
Uh,
Yeah. So you can do this for homework, right? This is
okay.
a little bit of maybe you can think, but it's now it's a very concrete question, right? And you can just think for 3 by 3 also and do. Okay. So
Okay.
yeah, but let me just make the question slightly more, correct. The question is obviously a little bit wrong, to be honest. Okay. So let me first write this, that phi is a group homomorphism. Okay. So you see, these two things are groups, right? Sn and GLNR are groups. So this is a group homomorphism. And once you show that this is a group homomorphism, then you would done in your group theory course that image of a group homomorphism is a group.
Image of a group homomorphism. Yeah.
Yeah,
So,
the image, because image may not be the whole codomain, right? But the image is also is a subgroup of the codomain. That you would have done in your group theory course.
yes.
Yeah. So if this goes, then this small thing sitting here is also a subgroup. That's a
the
nice thing.
subgroup. Yeah.
You want that, right? It's a nice thing. And that happens if this is a group homomorphism. So this is a group and the bada wala, this is a group. Okay. But this is not given to be a group, but it follows that it's a group because the image of a group homomorphism. Okay. So
And if
using
it is no, sure.
isomorphism, then it's a bijection. No, it's a bigger thing. Yeah. So the point is that this is the group homomorphism. So after this, so this will imply that image phi is a subgroup. I'm writing subgroup like this. Right? Subset is written like this. Subgroup is. Now I'm using more and more mathematics. Okay, it has to be. So image of phi is a subgroup of GLNR. This is already a nice thing, right? That we are showing this. The image of phi is a subgroup. And maybe you show it directly first if this is up to you. And then of course you can show that phi is an injective map. Okay. And that is easy. You can just show. Or if you want to use kernels and so on, you can do that. Yeah. So show that phi is injective, and then basically you show that Sn to then that basically means that this is a bijection, right? Once you show injective, it's a bijection, and this basically implies that that phi is an isomorphism onto the image, of course, not on the whole GLNR. Right? And that is why the initial question was sort of wrong in the sense that we had not even proved that that permutation groups form a group. But yeah, but it was understood. But anyway, okay. So this is the situation. This means that everything that happens there is sort of similar here. From Sn, you can understand everything that side. So it's just a way of writing it in a different, using different notation. Okay? There is no difference between these two groups. As abstract groups, there is no difference. So, but there is no difference that you over time you will understand, right? More and more, right? I cannot say I understand it completely, but I am not saying all that in advance. It's better to see it when the time is right. Okay, now we have shown this. So now the next exercise. So this is the homework. We write it and do it. And now the next
Okay.
things that I will ask probably will use this fact. So that's why we have proved it. So let's quickly go and then we have to be quick. So now you show that A transpose is A inverse, and A of course means a permutation.
P transpose equal to A inverse.
Nice thing, right? It doesn't happen.
And A is a permutation matrix.
Yes, A is a permutation. You can imagine this
Okay.
is your. Yeah, even that is a problem 5.3 in R10. Prove that inverse of a permutation matrix is true.
Any initialization? How to start it?
Yes. So so you can imagine that this A is the image of some permutation, right? You can imagine that this is the image of some permutation sigma. So now you can see. And because this is a group homomorphism, this inverse, yeah, what will this be? So if you write it, then you can understand. This is this, right? By
Yes.
definition, by definition. And you know that that's why we prove that things are group homomorphic, because we can do this. Right? It basically applying the inverse or applying the phi, they can be switched. Now you can try to use. So this means now it's very simple, right? So the inverse of a matrix, so inverse of a permutation, how will its matrix look like? We are saying that its matrix will be the transpose. Okay? Take a concrete example. Take a concrete example. So take the same example. Okay? Sigma equal to standard example 1, 2, 3. Take this example and you will see. So you already told me,
0, 1, 0, 0, 0, 1, 1,
right?
0, 0.
Now, what is sigma inverse? 3 to 1,
0.
just ulta.
Yeah.
Yeah,
Hmm.
just it's the opposite. Right? So if A goes to B, then B goes to A. That's how you get the inverse, because the composition will become A goes to A. So this thing, and now you tell me what's the matrix of this?
Then it will be that's third row. 1 minute. Okay. First row, third column is 1.
Right.
Second row, first column is 1. And
It
third
has to
row,
be there.
second.
Yeah. Right. So there has to be only one in every row and every column. Right. That also you know is true. Right. So now you can see that one is the transpose of the other.
Yeah.
So how difficult can it be to? It should not be very difficult to prove it now, right? It seems just like bookkeeping, not anything, not any maths. It's just writing.
Here I'm taking example, I can see it, but
Yeah. So now think why. Okay, so you take m sigma ka transpose, right? So m sigma, right? If the I comma sigma I entry, this entry is equal to 1, right? That is the meaning, right?
yes,
M
yes.
sigma में I comma sigma I entry is 1, right?
Okay.
Now, if you take transpose, then what entry becomes 1? Sigma I comma I entry becomes 1, right? And sigma I comma I entry is what?
That's m sigma's inverse.
That yes, right. You can say that, right? That sigma I went to I, correct? This means
हाँ,
right.
sigma I was हाँ ठीक है, sorry.
Right. So yeah, right. Sigma I went to I. Sigma I went to I, right? So you can say that, or you can just say that I went to sigma I inverse. Sigma inverse I, whatever. I of sigma inverse. Correct? This will true, right? I mean, so if in the okay, less than 1 minute is left, so we'll discuss this on the other side. Just think about it, and it will be now it's clear. I mean, but you think about this is not equal actually. This is for a different row. This is different entries, but yeah, but it's done almost. Okay, let's take a break and